So, good afternoon and welcome to today's physics colloquium. Uh, we are very happy to have Professor Eduard Vives from the University of Barcelona for as today's speaker for the physics colloquium. So he is here in IMSC related to the FracMeet program that we have been having since the last 1 week. And we have had very useful and interesting interactions related to failure on different systems. So Professor Vives has been in Barcelona, he just now told me, for 30 years now. So starting from his PhD days and some travels in between for postdoc to Denmark and other places, but again back in Barcelona for the last 20 years. And he has been doing a lot of work on related to failure questions. And today he'll be talking about generically on first order phase transitions and the avalanche dynamics and interesting features about that. So Professor.
Thank you very much. Okay, good afternoon, everybody. Okay, I just will repeat again that I am really very happy to be here. It has been a very interesting meeting this week. We got talks on many different subjects, but all of them related to the problems of fracture and these kind of problems, including material scientists, engineers, everything. So I learned a lot. And okay, when you offered me the possibility of giving this colloquium, then on purpose, I changed a little bit the focus of the talk. In that FracMeet meeting, I gave a talk on lab quakes. But here I thought that maybe I could, it's working?
Can you also switch off this?
I thought I could talk on something a little bit more general, which is this title. So it's avalanche dynamics in first order phase transition. Then the second part is not that important. It's just some examples that I will explain at the end. But I would like really to devote maybe half of the talk just to explaining this concept of avalanche dynamics using very simple concepts. So that's going to be almost an undergraduate lecture. So if you get bored, I'm sorry. But they told me that maybe it's better to have this kind of colloquium with concepts that are not very specialized and not very technical, but maybe people here which is not really in the field. Okay, well, this subject is related to what we have been studying in the University of Barcelona, I will say almost in the last 20 years. At the beginning, we didn't know that were avalanches, but then we changed the name of the subject, so all this started to be a special subject. And this work has been done in collaboration with these people here, which is the people that are permanent there in my group, Antoni Planes, Luis Mañosa, Teresa Castan, and also some other researchers that now are not there anymore. Xavier Illa is in Finland, Jordi Baró is in Barcelona, but in a mathematical institute, and Enrique Stern is in Cambridge. But of course, also many other people. I mean, some PhD students that did the PhD with me, some researchers from Mexico. Well, it's a long list, in fact. So we have got collaboration with many people. In particular, we do, as you will see, I am an experimentalist. We do experimental work, but we don't produce samples. So we need a lot of contacts to get samples for free, usually, to do the experiment. So the people in Argentina, Ricardo Romero, Marcelo Stipcic, they are producing samples for us for this kind of studies. Okay, let me see if this works. Okay, so that's the outline of the talk. There will be first just some kind of motivation. It's not even an introduction, just to show you some interesting aspects. Then I will go to this introduction. This is going to be basic thermodynamics, okay? Then I will explain you the kind of measurements we do. Is this acoustic emission technique, a little bit of how things are measured there. And then I have these different examples, but I will not go through all of them. I may just, depending on the time, give you two or three different examples, okay? So let's just start with this motivation. This maybe it's a motivation more thought for European countries, so I'm sorry for that. Maybe you will give me some other ideas, but what you see here, it's something written by Leonardo da Vinci in 1500. And I don't know if you know that Leonardo da Vinci was writing in a specular way. So it's impossible to read because this is written like if you were in front of a mirror. He had this ability of writing not only from left to right, that maybe many people do in different countries, but also that to read that you need a mirror. Okay? Nowadays we have computers, and it's very easy just to flip the image. And then you can read, but okay, it's also not easy to read because the letters on that and the paper is rather damaged. But here, with a little bit of effort, you can read that. But it's interesting, this plot here. What you see here is a prototype of a materials testing machine. You see, there's some kind of container that has sand on it. And then Leonardo was testing the resistance of wires. There's a wire here, and then he was putting some container, and then opening just very slowly, sand going in, and measuring the sand that was going in, and the length of the wire. So this was a first example of what many experimentalists are doing here. So this was a materials testing machine. Okay, and I think it's interesting. There's a remark here for engineers, because this machine, if you think of what it's doing is it's applying a force to the wire proportional to time. So the force is increasing proportional to time. And at some moment, these machines were like this, but then when they discovered the electric motors, these machines changed. And now what these machines, mostly of them, there are electrical ones and hydraulic ones, but most of them, what they do is to apply a speed to the ends of the wire. So they force a movement in a certain speed, and they measure the force needed for that. It's true that with electronics nowadays they can simulate this machine. So they apply the force needed to maintain. They apply the force speed needed to maintain a constant force, or a force increasing with time. But for some problems in materials, the speed of the electronics may be not good enough to imitate what's happening with this machine. So it's something important to know that these machines nowadays, the machines that are used for testing most materials, maybe they are missing some important details of the physics that is happening inside the materials. And, well, could be that what I'm going to explain today has some relation with this problem. Okay, this was just the translation. There is not much. Okay, this was the discovery of the fact that when the wire is longer, it breaks at a lower force than when it's, so the length of the wire changes the force. So the longer the wire, the force needed to break it is smaller, which is a little bit contradictory, but this is like this because of this breaking has to do with the disorder in the wire, and if it's longer, there are more points that can be weak points, so then it breaks before that, okay? Okay, so after this, another thing that I want to start, so the title, let me go back to the title. The title is this Avalanche dynamics. So nowadays there's many papers on avalanche dynamics, but this concept was, I would say, invented by Perbach in the beginning of the 90s or the late 80s, avalanches. And I just want to explain you what I think it's an avalanche and how do we recognize an avalanche, okay? Because if you, in your measurements, in your areas of research, you find this kind of behavior, you may have an avalanche there, or an avalanche process there. Okay, so usually materials, you can drive materials with different ways, with an external force, with an applied magnetic field, an applied electric field. You do some driving of a certain material, you pull it some way, and you try to do that very slowly, as slowly as you can, okay? And then you measure a response. The material responds with a deformation, with a magnetization, with a polarization, whatever you can measure, okay? And then you get some kind of curve that tells you how the material is responding. Typically, this response is a macroscopic parameter that you measure macroscopically, okay? In many cases, what happens is that when you are able to look in detail at a microscopic scale what's happening in this curve, you find this kind of behavior. You find that the system, in fact, there is periods in which it's not responding, and from time to time it has a fast response. Nothing responds, nothing responds. And the macroscopic curve is a sum, or It's the consequence of these many small jumps. Okay? This, you can already call these things avalanches. Okay? There is an important difference that the avalanches are microscopic, whereas this response is macroscopic. Okay? You can call these things avalanches, but I don't like to call them avalanches in general. To know whether these are avalanches or not, it's important to measure the sizes of these jumps. You measure the sizes, and then you make a histogram of these sizes. And then I think that one should really call them avalanches when these sizes are distributed with a power law like this. So you put log of the number of avalanches as a function of the size of the log of the size of the avalanches. If you get a straight behavior, then you are in front of such a distribution. And this is what then I like to call it really avalanches, because this is, for the people working in statistical physics, is an indication that you could be in front of a critical phenomena. And a critical phenomena doesn't have any characteristic scale. The only thing that you can do is to characterize the problem with these exponents, which are called the critical exponents. This is a critical phenomena out of equilibrium, but that is the signature that you could be seeing avalanches in your problem. In some cases, you find this law times an exponential of this kind. Then that could be, maybe there are avalanches, but there's something that is breaking this criticality, and this is something that you will see in some of the examples later. Okay? Why this exponent is important? This exponent is typically between one, a little bit more than 1, and hardly ever is larger than 3. Why it's important is because depending on this exponent, if you have this distribution, you can compute the average size of your jumps. You can find that when you integrate that between a minimum value and infinite, you can find that this diverges. Depending if the exponent is in the correct range, this might diverge. And this means that these avalanches, they are small, most of them are very small, but some of them can be infinitely large. Okay, and this, you could find in this macroscopic behavior, you can find some discontinuities. So you build a discontinuity just averaging things that are power law distributed. This is the scenario for avalanches that I think that is what you have to check to call a certain process an avalanche process, okay? So what I'm going to explain now in the introduction is just one of the possible frameworks for avalanches. It's a framework that was well established in the late 19th and 2000s. But it's not the only one. In fact, in the FRAC meeting, we have seen many examples of problems exhibiting avalanche behavior, which are not in this category, because this is going to be a category that we have a thermodynamics, we will have an underlying equilibrium problem that, for instance, in fracture, we don't have. We will have a first-order phase transition, and then associated to this first-order phase transition, we will see avalanches. But this is not the case always. So, I mean, this is just one scenario for avalanche processes. There are others, as many of you know. Okay? So let me then go to this kind of very simple explanations. Let me start with water, whatever you want. And you have a phase diagram, which you have pressure and temperature. And then you know this is, water can exist in different phases. But for instance, this will be the vapor or the gas phase. And here on top, you have the liquid phase, okay? We know that if we are at a constant pressure and we increase the temperature of the liquid, there will be a moment that we suddenly, the system transforms to gas. So we are crossing a first order phase transition, that is this discontinuity line. You can do also a similar thing just by keeping constant temperature and increasing the pressure from the vapor. You increase the pressure and then you condensate the fluid, okay? So first order phase transition can be crossed either by changing temperature or changing pressure. In this case, we use pressure to change the properties of this material because we characterize this water by the density. The density, or the inverse of the density, is the molar volume. So the gas has a high molar volume and the liquid has a low molar volume. This is what we call the order parameter. And the order parameter has a discontinuity in this first order transition line. You change from a high value of volume of molar volume to a low value of molar volume when you cross this line, okay? This is the idea of a first-order phase transition. It's not important for this talk, but this first-order phase transition, sometimes they end in a point that is a critical point that is not really important for what we will say today. And then above the critical point, you can go from gas to liquid without discontinuity, just moving like that, okay? This is the typical example that probably all of you know. I want to put in parallel to this example, two examples more, a little bit more complicated. Because I think in this case, even at the undergraduate level, there's people that confuses a little bit the concepts, okay? This is an uniaxial ferromagnet. An uniaxial ferromagnet, it does not exist, in fact, but it's an approximation. You should imagine a magnetic system with magnetic moments that are either oriented up or down, and then you have external field, you favor up or you favor down. In this case, the phase diagrams, the order parameter is the magnetization of the system. The magnetization is the order parameter, and the field coupled to the order parameter is the external field H, okay? When you increase the external field, you imagine that you start with the system magnetized down. You increase the external field, there will be a moment in the system flips and all the spins points up. This is the change of phase. So the phases here are a phase with negative magnetization, low magnetization, and a phase with positive magnetization. And the first order transition line is exactly at zero field. In equilibrium, is at zero field. So it's when you cross this line, you have the phase transition. This line ends in a point that is called the Curie point, above which you don't have discontinuity, okay? In many cases, people explain this phase diagram and says there are two phases, the paramagnetic phase here and the ferromagnetic phase here. But I don't like at all this, because then you cannot match these two diagrams. The phases here are positive magnetization and negative magnetization. These are the two phases that above the critical point, they are indistinguishable, okay? A third example, more complex, but maybe for many people, or what we heard these days, many people know. Martensittig transformations. This is a system which is solid, but it has some structural phase transitions. So at some point, the microscopic structure of the solid changes from being cubic to being tetragonal, or from being cubic to being another kind of symmetry. There are different Martensittig phase transitions. I am going to represent this by a very simple sketch here. I have a phase that is a square. So imagine that the atoms are organized in squares. This is the undeformed phase. And then this, at a certain moment, at a certain point, this system wants to shear, okay? And can shear like this because the atoms are better in this position. This kind of transition is this structural. There are many different kinds of structural phase transition. These are non-displacive, etc. These are called Martensittig transformations. Can be induced changing the temperature or changing the applied stress. So if you are, for instance, this is the Martensittig phase, the deformed phase. You increase the temperature. There is a moment in which the system goes back to the cubic phase, and it's not deformed. But you can also induce the transition starting from the cubic phase, this is, or the square phase in this case, increasing the external stress, you go to the Martensittig phase. Okay, this is a first order phase transition, also, like the other two, that separates these phases. Something that it's important to know is that, think again for the ferromagnet. Imagine that you have no applied external field. You are here. If you are here and you decrease the temperature, you will exactly sit on the transition line. What does that mean? It means that on this line, you can have coexistence of domains which are positive magnetized and domains which are negative magnetized. And this is what happens. If you take one of your magnets, you put it in the oven to very high temperature, when you go down, the system does not macroscopically magnetize, because half of the system goes one way, half of the system goes the other way, and in total the magnetization is zero. You have to apply a small magnetic field to select one of the two phases. Something similar happens here. When you are in the cubic phase or in the square phase, at zero applied stress, and you decrease the temperature, you cross this line, but then you sit here, and here you have coexistence of all the domains which are symmetrically equivalent. In this case, the two magnetizations, up and down, they are symmetrically equivalent, because if you turn the space, it's equivalent. In this case, you might imagine that to apply such a shear, you can do it in 4 different ways. You can do like this, 1, 2, or 1, 2. So you will have coexistence of these 4 of domains of this deformed like this. And this is indeed what happens in these systems. If you go to this picture, this is a copper zinc aluminum. This is a sort of brass alloy that has been transformed below the martensitic transition temperature without applied stress. And what you see here is that this is the surface, because these domains, the new domains, they reach the surface, and then they do some small deformations there that you can see using polarized light, okay? The different colors, every color is a different, it's called a martensitic variant, equivalent variant, just changing some symmetries, okay? In this case, okay, this is it's not a square, it's a real material. There are 12 equivalent variants that are here coexisting. In this plot, in this picture, sorry, in this photograph, you can already see the main message of my talk. If I ask you, what is the size? What is the typical size of a domain in this picture? What is the typical size of a domain? What will you answer? You see some domains that go from here to here, same color. Okay, so it's clear that the domains are elongated. This is clear. These are what's called martensitic needles, but the typical length could be this one. But then you see others that are like this. Okay, and then you see others that are smaller. And if I magnify, I will see others that are smaller. There are no characteristic size for these needles. You have all the sizes coexisting, and when you do a statistical analysis, you see that you have few large ones and a lot small ones. This is an indication of you could be facing a power law distribution of sizes. Just looking at this picture, okay? To explain this problem,
What is the equivalent argument for the magnet Ising model?
for the Ising model, you have to wait until the end. If you have disorder, I will come. I can write you the random field Ising model has Avalanche. This exactly the same. You will see when I finish this introduction. You will understand the mapping with the Ising model. But I will not put the Ising model here, but I don't want to do many maths. But you will see. Okay. How do we describe the thermodynamics of this first-order phase transition? We use something that is called Landau theory, or even more properly, Ginzburg-Landau theory. This is going to be really a cartoon description, but you can go more into the details of that and write field theories, etc. Okay? Imagine, let's consider the ferromagnetic case. So we have this phase diagram. We want to understand this line here, why the system changes from one phase to the other when we cross like this. But the same can be applied to the other cases. It's not that important. To describe that, we use what is called Gibbs free energy. So thermodynamics tells us that the system can choose values of the order parameters, can order in different ways, but it's always choosing the order parameter that minimizes this free energy. So the thermodynamic condition for equilibrium is to minimize the free energy. So then to describe a phase diagram like that, we can invent this kind of free energy functions. Here, what I represent here is this line is the order parameter. So in this case, is the magnetization. Okay? And then I invent a function that I say at high temperature, this function has only one minimum here. And at low temperature, this function develops two minimum, one here and one here. So the system, if there is no applied field, when you decrease the temperature, the system is looking for the minimum, is sitting here at high temperature. There is a moment when this becomes very flat that doesn't know what to do, but after that, the system either chooses to be here or to be there. The equilibrium there are two wells which are equivalent, so there are two phases with this value of the order parameter and this value of the order parameter which are equivalent, and they can coexist. Both minimize the free energy. And for that, if you write down this equation, this is very easy written like this. So this is a phi of m. You have a term which should be proportional to T minus Tc, m squared plus a term m4, okay, and B positive. This behaves like that, and when T is equal to Tc, this term becomes 0, okay, and is exactly the moment in which you have this flat point. Tc is the critical temperature or the Curie temperature, okay? This is without an applied external field. Now, so we are describing what happens in this line. Now we want to understand what happens when we put external field. When we put external field, if you think this free energy is symmetric when you change m and minus m. External field changes this symmetry. When you put external field, the system wants to magnetize according to the external field. So this we reproduce by putting here Hm, or H capital H. What is this term doing to this free energy? This term is tilting, is adding a straight line to this plot, which is what I represent here, okay? Here you have, when you have a positive magnetic field, you have this curve here on top. It's the same curve plus a straight line. So there is one well, which is the minimum one. The system, at this value of the field, will have positive magnetization in this side. Then, keeping the temperature below Tc, so keeping this shape, we start decreasing the field. So we are here, now we decrease the field. There will be a moment in which the two wells are equal. That's exactly when we cross this line here. And from that on, the minimum is here. So the system will have a discontinuity from this value to this value exactly when crossing here. You have an order parameter discontinuity. You jump from this well to this well. And then from that on, you keep being here. Okay, that will be a trajectory like this. Okay, that's the way we describe first order phase transitions with a Landau free energy method, okay? You can adapt these functions to any case, any kind of first order phase transition, putting more terms, less terms. There's different ways of playing with that, okay? And also, what Landau did, in fact, was to really come with some rules to which terms you have to include here, because this has to do with the symmetries of the problem. Okay, when these terms here are symmetric, etc., when you have some symmetry, for the case of structural phase transitions, this is much more complex. The order parameter is a tensor, and but you can discuss which terms should be there, and this is known and well solved, okay? Okay, so this explains this behavior here, okay? The phase diagram in a first order phase transition. And okay, I have plotted here the case of the simple fluid. What happens to the volume when you are above the critical point or below, you have the discontinuity. This scenario describes perfectly well this behavior. And the uniaxial ferromagnet that you were asking, so you have something similar. There is a detail here which is different, that is that when you are below, you change the field and you are below the Curie point, all the curves that describe how the magnetization changes with the field, they all jump at zero magnetic field, because this line is flat. For the fluid, this line is not flat, and then the curves, they shift in this diagram, because this is not at constant pressure. But since in this case we have this symmetry, this is flat, and then all the isotherms, because these are isotherms, have the discontinuity below a Tc, but at the same value of the field, okay? If you go like this and you decrease the temperature at zero field, you find something like this here. So you have zero magnetization, and suddenly two branches develop equally symmetric. So what happens is that the system fills up with domains of the two magnetizations, okay? So you can have two values. This is what happens in a first order phase transition. Okay, let me just jump this, it's not important. What happens, so what I explained it is the canonical thermodynamic description in equilibrium. What happens in reality? In reality, you go to phase diagram, you go to the handbooks of different materials that have phase transitions, and you see that this line, this famous transition line, is not a line. It's at least two lines, because these systems exhibit typically, first order phase transition exhibit hysteresis, what we call hysteresis. So you have one line like this. So this is now for structural phase transitions. So this is applied stress, this is temperature. You have a line like this that separates the two phases, but this line is different. When you go from low temperature to high temperature, you have the red line. But when you go from high temperature to low temperature, you have the blue line. So it's not, this is an indication that the system is not in equilibrium, so there's something wrong in my description, because this cannot be. This is not described by that picture. When that was equilibrium, when the two wells are equal, the system has to jump, and this is just one condition, not different. It doesn't depend on how you drive. But that's not all the problem. There's still something worse. That is that these lines, in fact, they are not lines. They are regions. So what we know is that when we increase the temperature, there is a moment in which the system starts to transform, and then it coexists. There is a region here in which the two phases coexist. The two phases meaning, in this case, the cubic and the one of the, or all the variants, they coexist until they finish and you are full in the cubic. Okay? This kind of is called the extended first order phase transition. This is called hysteresis. This is what they call extended. It's not on a line, but it's on a region. And similarly with the other line. The other line also extends. So typically, the phase diagrams of these systems that have first order phase transitions are like this one here. This is a nickel titanium phase diagram. This is two phases. One is the martensitic phase and the other is the R phase. And instead of giving you where is the line, they give you 4 lines. Okay, there is what they call the martensitic start, martensitic end, or austenitic start, austenitic end, depending on which direction you go, and start and end every time. So how can we explain this scenario? How can we explain this scenario? Okay, to understand that, we have to now go out of equilibrium. So we have to start to speak about time. Okay, time. First of all, one thing that we have to know is that these systems, especially first order phase transitions in solids, behave what we say it's athermally. How we understand that? Okay, imagine this double well that I plotted before. You were in this well was the best one first, and then suddenly you change the field, and the system should understand that has to jump from here to there because this is lower free energy, okay? How the system changes from here to here. There are three time scales to be considered here. One is what we call the typical thermal relaxation time scale. So the system, given the fact that there is a certain temperature, is fluctuating in this well, okay? It's fluctuating here with a typical time, tau thermal. Then there is the time that it takes the system. If the system reaches the maximum, the system will relax, but it will take some time to fall into the minimum. This is what we call the relaxation time, or I will call it the avalanche time. Typical time for relaxing from an unstable situation to a stable situation, very fast typically. But then there is another question, that is, we are driving externally the system. The driving, if you think about the driving is changing the barrier. If I go back, here. What I do when I drive with external field is to make this barrier smaller and smaller until it disappears, okay? So this I can do it faster or slower. And this is the typical time for driving. Sorry. So we have these 3 time scales. When do we expect hysteresis? We expect hysteresis when this limit here is fulfilled. So it's clear that the time for the relaxation is going to be very fast. The time for thermal fluctuations, this depends, but typically in solids, if we are at room temperature or below, this is rather short. So we can have even a range of driving rates that are between the 2 scales. And when you are in this range, you will find that what happens? The system doesn't have time to explore this minimum and discover the maxima, because this takes a long time, and you are driving this. So the system does not jump exactly when the 2 wells are equal. The system jumps when the barrier disappears. And this explains the hysteresis and the metastability, okay? So it's what I am plotting here. The system waits until the barrier disappears, and then only in that case it relaxes towards the new minima. And instead of having one jump, you have two jumps. You have, instead of jumping here, that will be the equilibrium, you have to cool more, or you have to decrease more the field. This depends how are you driving, or you have to increase more the field, or hit more in order to the transition to occur. Okay, so that is the explanation of the hysteresis, and this explains why in the phase diagram, instead of having only one line, I have two metastability lines. We call metastability because when the system is in this local minimum, this is not the global minimum, it's the local minimum, we say that the system is in a metastable state. The true stable state is not discovered until the barrier disappears. Okay, this is what we generally describe as an athermal behavior. So many first-order phase transition in solids, they behave athermally. And this explains why we have two lines. But we have seen that there are not two, there are four lines. So we need still an explanation for the extension of the transition. Why the transition doesn't occur at one point, but it takes some, you have to change the driving, keep going, in order for the transition to proceed. And for that, we need a new ingredient, which is disorder. Now, this is more difficult to do, but there are microscopic models like the Ising model that you were mentioning. When you add disorder, you can solve that really, well, the random field Ising model is called, you put some randomness there. But what you get is something which, like a cartoon, can be described here. Okay, this is a cartoon of what is happening. The idea is that when you put disorder, instead of having only two wells that you jump from one to the other, you generate many, many, many intermediate wells. If you have disorder and you have athermal conditions, then you are tilting that, you are driving, so you are tilting this, and the system jumps every time the local minima disappears, and then goes to the next one, and then to the next one, and then to the next one. But you have to drive it until you change the magnetization from positive to negative or vice versa. And this explains why the two lines are in fact regions. The transition starts here and ends here, and when you go up, it starts here and ends there. Okay? And this explains also why in this curved, this is supposed to have a certain slope, in these curved regions, when you magnify and look what's happening, you discover these steps, because these steps correspond to the jumps from one well to the other. And if there is a barrier, you tilt and nothing happens, nothing happens, nothing happens, and then suddenly, clack, something relaxes. You go to the next well, and you get this kind of behavior. So that is one of the possible scenarios for explaining avalanches, okay? So this is a sort of summary. When do we expect avalanches? We need a first-order phase transition. I think that this can be generalized to other problems, and this condition here can be changed by we need a certain instability. And I think that just generalizing phase transitions to instabilities, we can even take this scenario and put the fracture and other questions here. Okay, but this is more something to be discussed. We need disorder. Generally, we say quenched disorder, but even if the disorder is not quenched, things will be more complex, but we need disorder. And we need low thermal to athermal conditions, low thermal fluctuation. And in this case, then, we can justify the existence of two things. One, rate-independent hysteresis, this kind of hysteresis that you see here, this kind, or even this kind of hysteresis, is rate-independent in the sense that if you change the rate, if you don't hit this value and you don't hit this value, the curve will be the same. It's only when you approach here or there, you will start to deform the hysteresis loop. So this is not the typical hysteresis loop that you get when you go too fast, that the system has no time. In that case, it's just a matter of these two times, one against the other. Okay? But I'm saying that these two values are very far separated, so I can move in between, and then I have rate-independent hysteresis. This is the message. So that's an indication that you can be in this scenario. Rate-independent hysteresis, and then avalanche dynamics. So these are the framework that allows to describe this problem as
But when the first order transition and when disorder, wouldn't the transition become continuous? There's a theorem, the result says that the first order transition gets rounded off when it's disorder.
yeah, but this is athermal. You need the athermal. The system, in fact, is not in equilibrium. It's always in a metastable minimum. And it follows only the metastable minimum. In the random field Ising model, it's equivalent to say random field Ising model at 0 temperature. You write the random field, put 0 temperature, and drive with the field. The system will exhibit avalanche and power law distribution of avalanches. Sure. So it's athermal is the tricky thing. Effectively, it's as you were at 0 temperature. But it's not ground state, because ground state is the absolute minimum. It's local minimum. Okay, this is just 3 experimental examples of avalanches. In the late 90s, there were many experiments in which associated to first order phase transition in systems that were athermal, they discovered this kind of avalanche behavior. The first case was what is called Barkhausen noise in ferromagnet, so the typical hysteresis loop of a ferromagnet, like this. So you have, magnetization and field. If you have a technique that is able to really see in detail what's happening here, you discover that this is like that. Okay, and this technique is what is called the Barkhausen noise measurement, which is a technique that measures not the magnetization, but the changes in the magnetization. You put a coil, and every time there is a change in the magnetization, you have a coil, you get a pulse, and you measure the size of that pulse. This is the Barkhausen noise measurement, and this thing here is a train of jumps measured by this technique. Is a voltage in a coil when you drive very slowly the system, There were many, this was one of the first papers, but there have been many studies since then. There are groups that have done really very nice studies of Barkhausen noise, and they have characterized this avalanche behavior very well. This is the case where we participated, is these martensitic transitions in solids, in this case is copper-based alloys. And the technique now in this case is also a technique that is very sensitive to the changes in the strain. When there is a deformation in the system, that there's a small deformation, we can detect it. And this technique is acoustic emission. That is what I will explain to you now. But acoustic emission is almost exactly parallel to Barkhausen noise. But this is for magnetic systems. This is for elastic systems, let's say, for ferroelastic systems, if you want. And many more. So I have put here only the superconductivity problem. It's also avalanche-like. But there are many more. There's ferroelectrics. There's many more. Always an underlying first-order phase transition. Always an underlying hysteresis loop. Associated with that, avalanches in the hysteresis loop. So you always have this kind of scenario here. Okay? So let me now go to the, I don't know how much time I have.
15 minutes.
15 minutes. Okay, I will accelerate a little bit more, but let me just, this, in fact, I explained it, sorry, let me go. I explained it in the talk on Monday, but I will go a little bit faster. Let me jump over here. Okay, so what is acoustic emission? Essentially, when in a solid you have an interface, or in this case is like a lentil, that suddenly it becomes bigger, so there is a phase that grows, could be the martensitic phase growing. This produces, there's you plot here for instance, the volume as a function of time. You have a step, no? You have this jump, so this phase decides to grow, and the phase transition advances, so this volume has to increase. You have a fast jump. This fast jump generates an elastic wave that propagates and reaches the surface of the system. And here in the surface, what you get is a wave, a displacement, that in fact corresponds to the derivative of this change. So in fact corresponds to the speed of this change. So essentially what we do is to put sensors here that detect the waves that arrive due to the fast movement of internal interfaces. Okay, this is what we do in acoustic emission. It can be checked that integrating this function to the square power as a function of time, you can get an estimation of the energy. Okay, it's the energy that reaches your sensor, but that is a fraction of the energy that has been emitted somehow. Okay, this is the idea. Detect the energy, or the energy that is relaxed in this event. You remember that we go from one minima to another, we win some free energy, the system relaxes, and proportional to this energy is what we will measure, something proportional to this energy. Okay, this is how it works. So we put the sensors, we have the acoustic emission like this, we amplify, etc. We can also do what is called the location. If you can put many sensors on your sample and then take into account the time of arrival to every sensor, you can locate where the problem, where the phenomenon, where the source of the acoustic emission is placed. So in some measurements, we can use this location mechanism. Okay, then what we get, the data we get is just a series of pulses. Every pulse is related to something that happened there inside. And then from these pulses, we have to separate. There are different techniques to separate these in individual events. These events are called hits. It's true that, in fact, the voltage is never zero because there is some noise, etc. But you have to put a threshold and then separate these in hits. And then you can count the energy of every hit, etc. Okay? And by integrating, you can measure the energy, you can measure the amplitude of the hit, you can measure the duration of the hit, etc. No? So at the end, what you obtain with this technique is a series of events, of hits. Each one occurred in that moment. Each one has this energy, this amplitude, and this duration. And this is what we call a catalog. A catalog of acoustic emission data is just a list of the hits, and this is typically obtained when driving the system very, 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 very slowly. You start in one phase, you drive very slowly, you go to the new phase, and then you record this sequence of information, okay? And then if you do location, in fact, you have different sensors. When you detect hits in 4 different sensors, for instance, in this case, that was a 2D location, we could locate from these 4 hits, all these 4 are associated to the same physical event at the source with a certain algorithm and numerical processing. We can know where that was occurring. So we can see at what position was occurring. We can correct what was the energy at the source, what was the amplitude at the source. Okay? Then there are with this information, there's 2 important things that we can do. One is very simple. It's just what we call the acoustic emission activity, or sometimes it's called the pulse counting analysis, pulse counting. It's simply counting how many events you have per unit time. Only that, the activity, what we call the activity. Since we are driving the system, the number of events per unit time, we know the driving rate can be translated into number of events per temperature range, if we are changing the temperature, or per stress, if we are changing the stress, or per strain, if we are straining. So these are the 2 machines that I was saying in the beginning. You can drive like this or like that. Or per magnetic field, if you are in a Barkhausen experiment, number of events that you get when you change the magnetic field. Because you are driving with a certain constant rate, you transform that in this kind of information. This is one kind of analysis, but this will not discover the distribution of sizes, the distribution of energies. For that, we have to do statistics. We have to make histograms, put all the energies there, make a histogram, and check the distribution. So that is, you can do that with the amplitude, the distribution of amplitudes, distribution of energies, distribution of durations. You can do maps, histogram, 2-dimensional histogram, so distribution of amplitudes and energies, for instance, simultaneously, etc. And then with these curves, with this bad information, you have to check whether you have the power law or not. In some cases, as I told you, you find something which has an exponential correction, but there's a lot of statistical analysis here to fit this exponent, etc. And then also how we fit these values. There are different techniques. Some of them I explained it on Monday, okay? So now I have some examples, but let me show you some, maybe the ones that maybe are more interesting for people in the materials stuff, doing this kind of analysis. This is something that we did many years ago, which was just studying the martensitic transition induced by temperature. So here we change the temperature, we induce the transition, and this is a copper aluminum manganese alloy, okay? I don't go into the details. It has this transition from cubic to orthorhombic. The sample is very small. Usually for acoustic emission, we use small samples because, in fact, we want the sample to be size similar to the sensor to get as much energy as possible, okay? And we had different samples, well, different specimens, but so from the same sample, we cut different discs. They were this size here. And what we did is to drive the transition at different rates, and also to do what is called cycling. So we start, usually these samples can be put in the oven at high temperature, they homogenize, and then you slowly cool down, and you have what is called a virgin sample, and then you start, but still without crossing the transition, and then you start to cross the transition, back, forth and back, forth and back, forth and back, and then you study what happens when you cycle, okay? And this is just to show how the acoustic emission can reveal details of how this transition is processing, is advancing, okay? This is just, first of all, magnetic images. This is old measurements, but okay, these are images of the surface of the sample after the transition. Okay, you see the transition is similar to the first image I showed, but for this sample, okay, you don't see it very well, but here I have remarked what are the separations of the different coexisting martensitic domains. You see that this is after the first loop, so you just cross the transition and you have this image. You see that there are big domains of different martensitic variants. Then you do a second loop, so you go up and down, and then you get many more domains here. So the picture I show you was of this kind. It had many, many different domains. But this picture is not obtained the first time you cross the transition. You have to cycle it many times, and then at the end you get a sort of a stable parameter. In some cases, there are still big domains, but there are many small ones. And this, what we wanted to measure in this work is to check whether this somehow reaches a limiting structure, a limiting preferred distribution of domains, okay? Associated to this cycling, you can also measure, for instance, calorimetry. This is one advantage in first order phase transitions. That first order phase transition, when you cross a transition, you have latent heat. So you can put a calorimeter that if it has a good temporal resolution, you can see how the transition is advancing, because every time there is a new phase advancing, there is heat release. So, of course, the resolution you have with a calorimeter has nothing to do with the resolution you have with acoustic emission, because it's much, in acoustic emission, you reach below the microsecond scale, okay? When you do that, you can see how you can measure how the calorimetric measurements evolve with the cycling. You see that here, for instance, this one is very sharp, but then it develops some structure and it becomes something which has a certain structure. This is the width of the transition. So the transition starts here and ends here, okay? And when you hit, it starts here and ends there. It widens, okay? And you integrate these curves, you get the hysteresis loops, which are this one here that you see in this is the first time you have the transition, it's very sharp, but then it develops some structure here that already you see here, but this is in calorimetry. You see that it becomes reproducible after cycling. This is what is associated to what is called the shape memory. These systems, they have memory, but for the memory you have to train. And training is this cycling until the system learns what is the best path to transform. And this, okay, with calorimeter, this can be measured. You can measure some changes here, but acoustic emission gives you really a nice picture of what is happening. This is the activity as a function of the temperature. The first loop, you have something very sharp. The second loop, loop number 9, okay? And with these curves, you can compute really the mathematically the correlation, and then you see that when n advances, the correlation between cycle n and cycle n plus 1 is increasing. This is the learning. The system is learning how to transform from one phase to the other when you repeat this. Okay, it's training the system. And okay, this is, you can check that this is, with this learning process, if you go to the hysteresis loop, you can see that the dissipation of energy is decreasing. So the area here is much larger than the area here. So this learning is, the system is trying to find the best way to transform in order to dissipate less energy. And for that, what is the system able to do? Change a little bit the disorder. The system is relocating the vacancies, is relocating the dislocations so that this proceeds with less dissipation. Okay? Well, I don't know. I have 5 minutes. 5 minutes? Okay, let me go for another example.
What is the exponent for this, for that example?
Okay, I go to the exponent now. I have one with exponents. Okay, no, let me, okay. This is another, okay, let me maybe start with this one. This is iron palladium. Iron palladium has a cubic tetragonal phase transition, martensitic phase transition. We studied here a polycrystal and a single crystal. Just very fast, the message. This is calorimetry, but we go to the acoustic emission. So this is the single crystal. When you cool, it's plotted like this because I plot cooling and heating in the same curve, but of course the number is always positive. In calorimetry, it makes sense because one is emitted, latent heat has changes sign, but then just to compare, I plot like this. But when you cool, this is the activity. When you heat, this is the activity. And this is for a polycrystal. For a polycrystal, you cool and you heat. Okay, I'm wrong. No, this is the polycrystal, sorry. This is the polycrystal and this is the single crystal. When people was doing calorimetry in this problem, they were saying that the transitions, there was a hysteresis in the transition. You see here that there is, this curve seems to be shifted from the red, so, no, hysteresis, yes, but let's say, the starting point of this, when cooling is this one, and the finishing point when heating is that one. And here, okay, depends on how you put the line, but in calorimeter you have to put a line. It also seems that there is a shift. When you do acoustic emission, you get enormous resolution, and you can magnify the initial part, and then you put one of these thresholds, and you see that it's not like this. So this means that when you cool, there is a moment in which a small part of the system starts to transform, and this is exactly the same as when the last domain transforms back. There is not this shift. This was what we studied. Then if you study the distribution, okay, this is just the test of the rate independence hysteresis. This line, if you plot these curves here, now you change the driving rate, the curve changes. If you plot it as a function of time. But when you plot it as a function of temperature, and here you put not the number of events per time, but the number of events per temperature, the curves overlap. And this is what we tested here. And this is the test of rate-independent hysteresis. At different rates, you get exactly the same curves. If you go slower, then in time, one will expand more or less. But so the problem does not depend on the rate. That is a signature of being athermal, which is the case in these transitions, okay? Now let me go here. So this is the study of the distribution of, in this case, is amplitude distribution. You plot the histogram of the distributions. For the polycrystal, there is some problems there because polycrystals have some extra things in the crystal grains, etc. But for the single crystal, you get something very nice. You get this exponent here, 2.26, okay? This is, you can do the same analysis for many other alloys, and now I go to the very last, okay, this, well, I can show you more things, but let me go to the very last slide. Maybe this is the important message that they want to transmit. It turns out that when you analyze many structural phase transitions, In this case, we studied phase transition starting in cubic phase and going to different structures. You can go from cubic to monoclinic, from cubic to orthorhombic, and from cubic to tetragonal. This is the iron palladium I was showing. And different alloys in each case. And one can check that all the alloys that transform to the same low symmetry structure have the same exponent for the amplitudes and for the energies. This is the exponent for the distribution of amplitudes. This is the exponent for the distribution of energy. Not only that, when we have a transformation from cubic to monoclinic, we know that there are 12 equivalent variants. When we go from cubic to orthorhombic, we know that there are 6 equivalent variants, and when we go to tetragonal, we know that there are 4 equivalent variants. Okay? No, this is wrong. This is a 3. This is a 3, sorry. This is a 3, yeah. Tetragonal, you can vote like this, or like that. This is a 3, sorry. But okay, anyway, if you see the exponents are not the same, the exponents depend on the symmetry of the low temperature phase. Because what is the exponent associated? Why the exponent is changing? Because the exponent has to do the relative weight of the big avalanches to the low avalanches. When the system has more variance, it finds more paths to transform. It's more easy to transform and finding smaller regions without having the big avalanches. So then you have more small avalanches and less big avalanches. This means a larger exponent. Okay? 2 for energies. When you have less possibilities, the system is forced to wait until it can grow in that direction because there's only 3 possible directions to grow. So it has to wait until it can relax towards that path. It cannot do another thing because there are only 3 ways of advancing. And this forces it to have larger jumps. And then you get lower exponents. So the exponent changes with the symmetry of the low temperature phase. And this we tested with many, so you have here all the collection of experiments we did. And we were testing that with all these cases here. Okay, and well, with that, I mean, there are many things that I could explain, but I think I will finish here. Thank you very much for your attention.
Very interesting and illuminating talk. Questions? Yes, Massimo.
So, two questions. First one, the distribution is the distribution of all the avalanches that you observe.
Yes.
But the system is not in a steady state, right? Because
You are in a stereosis loop. In the beginning, it could be different. Then you have the medium part, which is more or less, you can think it's a steady, and then the end, it saturates there. And then you can say, okay, the distribution of avalanches can be different in the different parts. Okay. You are... if you, I mean, there are 2, let's say. One, you can measure the exponent only in the moment in which the fastest slope is when you are in the middle of the transition, exactly at the critical field, then you have exponent. What you have when you integrate the whole branch is also critical. It's a different exponent. One is what is called the cumulative exponent, and the other is the exponent exactly at the transition. But it's also critical because it inherits the critical behavior of that part that dominates the whole. But there is a shift. This was already discovered in the first model, on the random field Ising model exactly. The people always talk about 2 exponents. The one that corresponds to the middle of the internal part of the high hysteresis loop and the integrated one. What I show here are integrated exponents.
other question, this is what you measure after many loops, so
Yeah.
in steady state. Otherwise, it's changed with time, the exponent.
Yeah, this I jumped too fast, but yeah. In fact, what happens is that when you have not cycled, the distribution is not power law. It has an exponential correction. Let me show. What is it? Okay, so more or less is what I show here. So in the first loop is this one here, the distribution of avalanche, and then when you increase the cycling, it gets more and more power law. Then what we do is this is not very nice, but when you feed this to this model, to a model that has a lambda correction and an exponent, you find that with the number of cycle, these things change, and when you get the stable solution, lambda is 0, so you are critical, and the exponent has this value, which is the, let's say, universal one. But before, what you get is something, okay, you can get that the exponent is changing, but it's not true, because it's not a power law, because lambda is not 0. So the learning process, it's also a learning process towards critical situation. The critical distribution, the power law distribution, is the one that minimizes the dissipation of energy in the loop.
Can I ask another question? Okay. So the previous slide, I guess, there was the correlation. The correlation is increasing. What's the limiting value? It goes to 1?
To 1. No, but by definition, it's 1.
No. As a function of n, do you reach the limiting value 1?
No,
but it doesn't become deterministic.
It's very low, in fact, here.
Yeah, so
it increases, but it's low. It's because, I mean, there are many experimental problems here. I mean, you don't detect all the, you have a threshold, you don't detect all the avalanches, you have cutoffs.
Just out of curiosity,
you have deformation of
I guess people have studied these things also in numerics, where you don't have these artifacts. Or
yes, for it. Yeah. Well, I don't think there are models for. Well, there are some simulations for this process of learning. Aluwalia, maybe he's from India. Aluwalia. He did some simulations, including, but that was for a sort of a random field model, but including mobility of the random fields, some readaptation of the random fields. Every time that the one part changes the magnetization, the random fields there are readapted, and he explained this. So what happens is that in principle, disorder is quenched. If disorder is quenched, you will never have this evolution. But with quenched disorder, you cannot explain a learning process. What happens is that there is some mobility, not very much, but some mobility. When the front advances, it rearranges few. Few of the disorder is rearranged. And where is it put? This disorder moves and goes where? To the place where it will minimize the energy dissipation. So somehow the system is trying to optimize the jumps it's doing to do things more easy without going to very high barriers. It's looking for the paths in the free energy that have, and if I can just kick a little bit the stone to have a lower path, I do it, and then I pass. And by this, it's optimizing. But you need some disorder, and then when you hit up and you erase all the disorder, you erase the learning process, and the system has to start to learn again.
No questions. From the mission, is it possible to find out where the avalanche occurred?
Where? Yeah.
And if yes, then in the distance between two successive avalanches, is it a power law too?
We have done that only in one dimension, I show you. And this is also very interesting because it's something that the acoustic emission can be coupled to any testing machine, and it gives a lot of information about what is happening. Let me show you. I think one of the examples I wanted to show is this one. No, not, okay, this was the machine of Leonardo. So this is the hysteresis loop that you obtain when you do force-driven or speed-driven. In one case, you have yield point, and the other, you don't have yield point. Okay, the engineers plot this 90 degrees around, but this is the two loops. One is more internal than the other. The blue one is obtained by controlling, so you put a speed. And the black one is when you impose force proportional to time. Okay, but it was not the question, sorry. Let me just go, the other one. Okay, so here in this case, when we do the experiment in the tensile machine, we put two transducers. And with two transducers, just looking at the time delay of the signals, you can know where it was. Okay, and then you can see these things. This is time, where we are pulling here is soft-driven means force proportional to time, and this means speed, constant speed. And we are pulling, this is Z, the position of the event, as a function of time. And what you see here is that, okay, there's nothing here, then you start to have events in the upper part of the sample, because this is the upper part, but these events, they concentrate like here. And there is another thing here that moves like that, okay? And then it stops, it finishes. This corresponds to, where is it? Okay, maybe you can see it here. I don't know if you see, but there are two transformations. Given this is single crystal, given the orientation, it forms two domains here that when you load, they move like that. And then when you unload, that is what I was plotting, they move slowly towards the center. And the avalanches occur here, exactly here in the interface. And it's what you are seeing in this plot. And this is first cycle, second cycle, third cycle, etc. And this is hard-driven and soft-driven, and it's not exactly the same. Even the distribution of energies is different.
So if you plot the distance between two successive avalanches, does it show some?
We haven't, in this context, we haven't analyzed that. We did this kind of analysis for the porous materials, and this we have a force, one of these analyses, correlating the avalanches with the force drop. But here we haven't. Okay, but what is nice is that, for instance, here, when magnifying this part, you can discover this kind of lines, and this is because the transition, well, let me show. The transition it's advancing like that. So this is the martensitic, this is the martensite, and this is the austenite. Well, when you load, when you unload, so it's not advanced like that. It advances creating some needles like this that advance and fill. And then it creates a new one here. This grows like that. And when you project that into the Z direction, you see activity here, here, and here. So you see, at the same time, you see activity in three places. Are the needle tips that clack, clack, clack advance. And we can measure the distance between the tips, etc. And then you can find, for every event, the energy at the source, and you can plot your hysteresis curves. These are the hysteresis loops. Sorry. Okay? But when you detect an event, you put a symbol with a color that is proportional to the energy of that event. So, for instance, here you discover that when you go back, you have more acoustic emission with larger energy in this part. Okay? And vice versa. For instance, this when you do the driving by the speed, you have this, you have the yield point, and here is where you have most of the large avalanches, the red stuff. And then you have the plateau, okay? And this is let me check. No, sorry, this is the going up, is this one? And going down is this one. So it's at the end. In this case, you have a sort of re-entrant yield point. So you have yield point when you go up, when you load, and yield point when you unload.
Any more questions? Yes.
So the lines in the earlier plot, do it correspond to the shear bands or the slip lines?
No, none of the two. This is a first order phase transition. This is a different phase. This is martensite, and this is austenite. So it's the martensite advancing in the austenite. And it's known when you have the symmetry of the austenite and the martensite that the interfaces can only occur because there is no diffusion here. So the atoms are always in the lattice. They can only occur in certain lines with a certain angle. This angle can be perfectly calculated. Because in this case, we are growing only one variant, the one that is favored by this force, by the stress that we are applying. In this case, given the orientation of the monocrystal, there is only one variant that grows. Well, if there's somebody that works with martensitic transformation, could be one variant or two, because sometimes this martensite is what they call twinned martensite. So maybe this is two variants, but this is another question.
More questions? If not, let's thank Eduard for a very nice talk. And also
Thank you very much.